We present BallpitNDF, a full-stack, deep perception robotic manipulation system that utilizes a few-shot imitation learning paradigm for pouring tasks.
Pouring is one of the most commonly executed household manipulation tasks in our daily lives. A successful pour, however, requires both a successful grasp of the surrounding container and successful pouring dynamics on a wide variety of object shapes and configurations. Can a robot robustly perform pouring on objects outside its demonstration distribution and in novel poses?
To that end, we utilize local neural descriptor fields for the pouring task. Due to the lack of fluid simulation in Drake, for our project, we focus mainly on the task of pouring discrete objects, namely balls, into a ball pit. Neural descriptor fields are a set of category-level pose descriptors trained on the surrogate task of object reconstruction to find suitable grasp poses. These descriptors encode the spatial relationship of the pose with respect to the target object geometry. They are also trained to be SC3 equivariant, i.e., robust to arbitrary rigid transformations of the target object.
These descriptors allow for grasping on objects in arbitrary poses through an energy minimization scheme. Given a set of demonstrations of grasping, we can optimize the pose relative to the new target geometry so that the descriptor values match.
Neural descriptor fields suffer from being mere category-level descriptors, however, and cannot generalize to out-of-demonstration distribution object categories. Local neural descriptor fields, on the other hand, use a voxelized encoder so that the descriptor values are localized to local geometries rather than the global ones, allowing for out-of-category generalization. We now discuss our model pipeline. Our pipeline consists of three main modules: a deep perception module for object detection and segmentation, a grasp selector using an energy minimization scheme with local NDFs, and a kinematics planner using off-the-shelf differential IK.
Our simulation setup consists of a Franka Panda arm and a set of 3 RGBD sensor cameras that get captures of the target container. This is done by first getting the bounding box of the basket using the recently proposed grounding dyno algorithm with a prompt for the object class. For example, we prompt the network a basket with a handle for baskets. Due to the infinite depth of the corners of the bounding box coordinates using just grounding dyno, however, we get the minimum and maximum depth values of the points on the target object by segmenting out the object using the segment anything algorithm with the same prompt and adding a small offset.
We found that just doing this, however, can lead to major errors due to imperfect segmentations near the object boundaries. We thus perform statistical outlier removal using the k-nearest neighbor metric before unprojecting and merging the point clouds from the three cameras. We then utilize an energy minimization scheme using the aforementioned local neural descriptors. We first give the robot arm a demonstration of grabbing 10 different mugs, and then utilize the local neural descriptors to find grasps on the novel object geometries. We then use off-the-shelf differential IK solvers with the simple state machine planner to do the final pour.
We tested our system on 3 distinct object classes, namely baskets, bows, and mugs that differed from our demo distribution mugs. Overall, we found that our robotic manipulation system was capable of grabbing and pouring objects successfully on all 3 object classes. All demonstrations are sped up at 3 times speed.
To quantitatively assess our system, we ran the pouring task on the 3 different object classes for 100 iterations each. Ultimately, we found around a 75% success rate, average across all 3 tasks, with more success on basket handles, which were pretty similar to mug handles, compared to bowls, which had handles that differed significantly from the geometry of the mug demonstrations.
Although our system generalized quite well to several different novel object classes, the system was not always perfect. Some of the most notable failures included perception failures due to poor prompting in the perception networks, grasping failures due to the on-demand optimization of the query points used in the local NDF, and kinematic failures due to the object geometry being collided into during any of the intermediate phases.
Despite these limitations, we believe that this work provides a valuable stepping stone in the pursuit of future generalizable full-stack pouring systems. To that end, we have released our code publicly on our GitHub repo for others to build off of.